Hey there. This is Heath. I hope you are warm and dry wherever you are and not stuck out in this awful weather. We're looking at day 6 today, which is selecting with repetition. Let's go ahead and get started. We're starting with an example today. We are working in a soda warehouse that has 5 different kinds of sodas: Cokes, Diet Cokes, Sprites, Pibs, Fantas. Um, and customers can create customized 12 packs. They just an empty box, and they can put mix and match whatever they want to for their 12 packs in this warehouse. It's kind of a nice thing to be able to do for a customer. So a customer could come in and make a 12 pack that has 6 Diet Cokes and 3 Sprites and 3 Fantas, and then check out with that 12 pack. So how many possible 12 packs are there? So we're making the assumption that nobody cares what order the sodas are arranged in the 12 pack. It doesn't matter if there are 3 Fantas on the bottom row or the top row or middle row of the 12 pack. It's just that we're looking at the contents of the 12 pack. So 10 Sprites and 3 Fantas are different from 9 Sprites and 4 Fantas, but I don't care how they're arranged inside there. Since we don't care how they're arranged, this is going to be a combination problem and not a permutation problem. So this is a combination and not a permutation. But it's different from some of the combination problems that we've seen before, because every soda is eligible to be chosen over and over and over again. Last week when we were looking at combinations, we did the problem, for example, where we had 10 athletes and we wanted to pick a committee of 3 athletes. But if I've chosen Serena Williams to be on the committee, I can't choose her to be on the committee again. There's only one Serena Williams. But here I could choose out of my 12 pack 3 Cokes and 4 Sprites and 2 Diet Cokes and a Fanta, or something like that. I mean, I can choose multiple copies of the same thing now. And so, how are we going to do this problem? The other thing I want to suggest is that we follow the advice from last week of coming up with an algorithm to create these different assortments instead of trying to just start writing down numbers. This turns out to be an easy formula, but it's not the formula you would think it would be right at first. I mean, the kinds of things that people tend to try are things like, well, there are 5 different possibilities for the first space and 5 different possibilities for the second space and 5 different possibilities for the third space, so it might be 5 to the 12th. But that gives us a permutation answer, because putting a Coke in the first space is different from putting a Coke in the second space, for example. And so we want to come up with an algorithm for this. And so here's the strategy I'm going to have, is that we have a robot that is packing this soda for us. Okay? So we have this robot. With a little grabby arm here and a box attached for putting sodas into the box. And the robot can grab from aisles that have an unlimited number of Cokes. So there are, all these cans of Cokes. Then what is the next one? Diet Cokes. And then Sprites. and so on and so forth. Let's see, the next two are Pibs and Fantas. All right. Well, our robot is primitive. It only knows two commands, and the commands are: one, grab a soda and put it in a box. And move forward one space to the next type of soda. And then at the very end, there's a table where the robot can put the finished box. If the robot advances to the table, the robot will immediately dump the box onto the table and come over here and reset itself for a new order. Okay, that's the idea. So it doesn't have to have a command. Let's call this command 0 instead of command 2, so that we can do these as strings of bits. That the ability for the robot to unload the box and then start over here with a new empty box is hard-coded into the box. It's hard-coded into a robot. So if the customer wanted, for example, 3 Cokes, 6 Sprites, and 3 Pibs. Okay. Then the instructions to the robot would be to grab 3 Cokes and put them into the box. Then advance one space. Now the robot's at the Diet Cokes, but the customer doesn't want any Diet Cokes. So we advance again. Now we're at the Sprites. We'll grab 6 Sprites. We'll advance again, and now we're at the Pibs. Then we'll grab 3 Pibs. Then we have to advance to the Fanta, and then we have to advance to the table. Okay. So once we advance to the Fanta, we don't grab any sodas, and because the box is full, the robot dumps everything onto the table. That's the idea. Okay. So this is a recipe or an instruction for how to grab 3 Cokes, 6 Sprites, 3 Pibs. Okay. Let's say we wanted 2 Diet Cokes, 1 Sprite, and how many are left? 9 Fantas. Okay, the robot starts over here at the Cokes. We don't want any Cokes, so we immediately advance. We're now at the Diet Cokes. We grab 2 Diet Cokes. We're done, so we advance, and now we're at the Sprites. We want 1 Sprite. Then we advance, and now we're at the Pibs, but the customer doesn't want any Pibs. So the robot advances again to the Fantas and grabs 9 Fantas. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? So the specification that we're looking at here is that a complete order must have 12 ones. Because 12 sodas have to be grabbed and put in the box. and 4 zeros. A 0 to move from Cokes to Diet Cokes, a Coke 0 to move to Diet Cokes to Sprites, 1 to move from Sprites to Pibs, 1 to move to Fantas, and Fantas are at the end of the line where the table is. So that even if the customer only wants Cokes and Diet Cokes, we still have to advance the robot over to the end of the line. And so the complete order also has to have 4 zeros. There are 5 kinds of sodas, but we only need 4 zeros to do the advancing because there are 4 transitions from one to the next. So a complete order will have 16 bits, 12 of which will be 1, 4 of which will be zeros. And so if we choose where the 1s go, we get 16 choose 12. We could also choose where the zeros go. That would be 16 choose 4. But these two are equal to each other by the symmetry law. So figure out what the total number of bits in the correct order is, and then decide whether we're choosing the 1s or choosing the zeros, and then list how many of those that we're choosing. The 1s will be the number of sodas, and the zeros will be 1 less than the how many types of sodas there are. Okay? Are we good? So this is the correct answer, but the idea where the 16 comes from is not immediately obvious in this problem. It is the number of sodas in a 12-pack plus the number of transitions from one soda to the other kind, which is 1 less than the number of types of sodas. Okay? So let's try this different example. A donut store carries 5 varieties of donuts. So the number of varieties is the same as the last problem. We have 5 kinds of donuts. Chocolate, maple, Boston cream, powdered, and jelly-filled. And so our robot starts over here, starts to pack the box. Grabbing donuts off the shelf, putting them off the box. When the robot gets to the end of the row, unloads the box on the table and resets. If Chris wants to buy 8 donuts from the store, then a correct order will have 8 1s for the 8 donuts Chris is going to buy, and we'll have 4 zeros because there are, among these 5 varieties, 4 opportunities for the robot to move. 4 zeros. And so that's a total of 12 bits where we have to choose the 8 that are 1s. Or the 4 that are zeros. Either one. Okay? All right. So we have a theorem for this. This is the theorem from the book, that if we're choosing R objects from N types of objects, where any object can be used as many times as desired, the combination is the number of objects plus the number of types minus 1, choose the number of objects that we're choosing. So it's N plus R minus 1, choose R. Okay? It's an easy formula, but again, it's not an obvious formula until you think of an algorithm for how to pack all these boxes. I'm using the robot metaphor here, but there's other ways you could describe this. Okay? All right, so we have an unlimited number of jelly beans now that are available in 5 different colors. So we still have the number of types is still 5: red, green, yellow, white, and black. And we want to select 20 jelly beans. So a complete order will have 20 1s and 4 zeros. So we need 24 bits, and we will choose 20 of them to be 1s. Okay? And again, you can also say 24, choose 4. How does the problem become more complicated if we have to select at least 2 jelly beans of each color? If there is a minimum requirement, like there is in this box, we just pre-fill the box with that requirement. The robot doesn't start with an empty box. The robot goes ahead and starts with 2 red, 2 green, 2 yellow, 2 white, and 2 black jelly beans. And therefore, the robot doesn't have to worry about this. We pre-fill the box. And then we're only selecting, since 10 boxes of jelly beans are already chosen, jelly beans are forced. We have to have 2 of each of these 5 colors. We're really only choosing 10 more jelly beans. More jelly beans. And so a complete order will have 10 ones and 4 zeros. And so we'll be just looking at 14 choose 10 instead of 24 choose 20. The other 10 jelly beans are forced on us because we have to have 2 of each color. All right. So if we have a minimum requirement, we preset the box with that minimum, and then we're only choosing what's left to fill out the rest of the order. All right, let's try another example. 2 different lottery systems are proposed. In one system, players select 6 different numbers from 1 through 50, and they have to be different. So 1, 2, up through 50, but no repeats. In the second system, players can select only from 1 to 45, but they may select any number as many times as they want to. Which system has more possible lottery tickets? Which system is going to be have more variety in the possible number of winning tickets here? So, do you have an idea? Do you have a guess at what the answer is going to turn out to be? Well, 50 repeats here, or 50 numbers with no repeats, that's just a standard combination problem. And the answer is 50, choose 6. There are 50 numbers to choose from. We have to choose 6, and all 6 of them have to be different. Here, what we have is we are choosing 6 numbers, and there are 45 numbers to choose from. And since we can choose a number multiple times, it's like having 45 different kinds of soda or 45 different kinds of jelly beans. And when we're building our lottery ticket, we can tell the robot to go to number 3 and say, I want that number 4 times on my card, for example. And the robot pulls down 3, 4 times. That's kind of the idea here. And so a complete order will have 6 ones and 44, 1 less than a number of different kinds of bins, zeros. But 44 and 6 turns out to be 50. Choose the 6 ones again. It turns out that these 2 systems have exactly the same number of possible tickets. That's not obvious, but they turn out to be exactly equivalent in terms of odds. Okay. All right, let's do 2 more examples and then we'll wrap up. This is a polynomial problem. We're expanding a plus b plus c plus d raised to the 7th power and then combining like terms. How many terms appear in the expansion? So, for example, some of these terms, b to the 7th, and one of them would be a to the 4th, b, c, d, where the exponents add up to 7. 4 plus 1 plus 1 plus 1 is 7. Or b squared d to the 5th, or a squared c to the 4th d. 2 plus 4 plus 1 is 7. How do we count all of the different possible terms? This isn't asking for the coefficient now. This is asking how many terms. Well, we have 7 exponents, and they have to be distributed among 4 variables, and we can have a variable as many times as we want to. So this is like saying that I have, a robot filling a box that holds 7 exponents, and grabbing, say I'm going to put an exponent on A, and then 1 on B, and then 2 on C, and then 4 on D, for example. And so a complete order will have 7 ones, and since there are only 3 transitions in this system, 3 zeros. And 7 and 3 is 10. 10 choose 7. So how much is that? That's 10 times 9 times 8 over 3 times 2 times 1 is, I think, 120 terms. That's a large number of terms, but we now know for a polynomial we can figure out not only how many terms, but we can also figure out what all the coefficients for these things are. We're learning to replace FOIL with something more sophisticated, and something powerful enough that we can automate it and come up with polynomial expansions relatively quickly. All right. Last question. Find the number of lists of the form x1, x2, x3, x4, x5, where each xi is a non-negative integer, and x1 plus x2 plus x3 plus x4 plus x5 has to add up to 12. Okay? So, again, some of these lists are I need 5 numbers that add up to 12, and I'm not allowed to have negatives. So I could have, for example, 1, 2, 3, 4, 2. Or I could have 0, 6, 0, 3, and 3. Those add up to 12. Or I could have 11, 0, 0, 1, 0, and so on and so forth. So how do I generate this? This we can model also using a robot. We could go the other way around. If I think of these 5 spots as like 5 bins, so here's x1, x2, x3, x4, x5, and this time instead of the robot picking things and putting them into a box, the robot has 12 objects. I can't draw robots, by the way. Here's my box, and my box has 12 objects in them. And I'm instructing the robots to start putting these objects in these bins. So if the robot puts 4 objects into this bin, and 2 objects into this bin, and 5 objects into this bin, and 1 object into this bin, then that would give me a listing. That's the idea. So instead of a 1 being to grab an object from the bin, it's actually to place an object back in an empty bin. And so a complete order will have 12 ones and 4 zeros. And that's 16, choose 12. Okay? Which is actually the same answer to the very first example we did, involving buying a 12-pack of sodas when there were 5 kinds of sodas. I can think of these lists as the number of possible Cokes, Diet Cokes, Sprites, Pibs, and Fantas in an order. And this question is asking how many just sets of numbers are there. Well, that's actually the same kind of thing as saying how many different ways can we pack a 12-pack with 5 different kinds of sodas. Okay? All right. I hope this helped. Y'all have a great day. Hope the weather warms up a little bit. I'll see you guys Wednesday. You take care.